Hello everyone. This presentation introduces Team 6 final project, hip extension torque control for H10-based squat lifting assistance. The project uses the H10 hip assistive robot to support squat-based lifting. The goal is to detect the rising phase of a squat and provide hip extension torque at the proper timing. The presentation consists of 4 parts: scenario, sensors, algorithm, and analysis. The target scenario is parcel loading and unloading. Since the experiment was conducted with healthy student participants, the scenario focuses on an industrial assistance task rather than a patient-specific motion. In parcel loading work, workers repeatedly lift boxes from a low position. This motion can accumulate fatigue in the glute muscles, hamstrings, thighs, and lower back. Among these muscles, the glute muscles are especially important because they strongly contribute to hip extension during the rising phase of a squat. Therefore, this project aims to reduce the physical burden during lifting. The robot detects when the user starts standing up and provides hip extension assistive torque during the rising phase. 2 main sensors are used. The first sensor is the left and right hip joint encoder inside the H10 robot. The encoder measures the hip joint angle, and this signal is used to detect the squat and rising phases. The second sensor is external EMG attached to the left and right glute muscles. EMG is not used as the assistance trigger. Instead, it is used to evaluate whether assistance reduces muscle activation. In short, the hip encoder is used for phase detection, and EMG is used for effectiveness evaluation. For the hip encoder, zero calibration and sign correction are applied to obtain the hip joint angle. In this convention, hip flexion is positive. So, when the user squats down, the hip angle increases, and when the user stands up, the hip angle decreases. The hip angular velocity is calculated by differentiating the hip angle every 1 millisecond. Because differentiation amplifies noise, a low-pass filter is applied. The hip joint angle and angular velocity are then used together for phase detection. For EMG, the relaxed state bias is first removed. Then, the signal is processed through an 80 Hz low-pass filter, full-wave rectification, a 5 Hz envelope low-pass filter, and deadband processing. The final output is the muscle activation envelope. The squat lifting motion is divided into 4 phases: stand, down, sit, and up. The target phase is the up phase, also called the rising phase. The rising phase on condition has 2 main parts. The first condition is angle_OK. This checks whether the user is already in a squat posture. If either hip angle is larger than the threshold, the system considers the hip to be sufficiently flexed. The second condition is vel_OK. Since hip flexion is positive, standing up means that the hip angle decreases. Therefore, the hip angular velocity becomes negative. The rising phase is turned on only when the user is in a squat posture and the hip joints start moving in the extension direction. This helps prevent false triggers caused by small posture changes or sensor noise. Once the rising phase is detected, it is latched. This means the phase does not immediately turn off even if the sensor values briefly fluctuate. The rising phase turns off under 3 conditions. First, after the minimum rise duration, if both hip velocities return close to 0, the system considers that the rising motion has finished. Second, if the rising phase lasts longer than the maximum duration, it is turned off for safety. Third, if the control is turned off, the rising phase is immediately disabled. This latch and release structure allows the robot to assist the actual rising motion without rapidly switching on and off. For analysis, 3 evaluation metrics are used. The first metric is rising phase IEMG reduction. The glute EMG envelope is integrated during the rising phase, and the IEMG values are compared across torque conditions. The second metric is assistance timing error. This evaluates how well the assistive torque timing matches the actual rising motion. The third metric is hip extension motion smoothness. For this metric, hip acceleration RMS and commanded torque rate RMS are checked. For experimental conditions are compared: 5 Nm assist, 7 Nm assist, no H10, and no assist. The no H10 condition is a reference without wearing the robot. The no assist condition means wearing the H10 with 0 Nm torque, and it is used as the formal no assist baseline. The 5 Nm assist condition shows squat lifting with 5 Nm hip extension assistance. In the graph, the hip angle and angular velocity show the squat and rising motion. When the rising phase is detected, the rise flag becomes active, and assistive torque is applied during the lifting phase. The 7 Nm assist condition shows the same task with a higher torque level. The graph shows that the rising phase is detected during upward motion and that the commanded torque is activated during that phase. This condition is important because it produced the largest reduction in glute muscle activation. The no H10 condition shows squat lifting without wearing the robot. This is a reference case with no robotic assistance. The graph is mainly used to observe the GLID EMG response during lifting, since there is no H10 torque command. The no assist condition shows the user wearing the H10 robot with 0 Nm torque. The robot is worn, but active assistance is not provided. The graph shows hip motion and EMG response while the torque command remains 0. This condition is used as the baseline for comparison with the 5 Nm and 7 Nm conditions. The quantitative results are summarized as follows. For rising phase IEMG, muscle activation decreases as assistive torque increases. In the 0 Nm condition, the right and left IEMG values are 0.283 and 0.255. With 5 Nm assistance, they decrease to 0.102 and 0.130. With 7 Nm assistance, they further decrease to 0.073 and 0.084. This corresponds to a 74% reduction on the right side and a 67% reduction on the left side in the 7 Nm condition. For timing error, the 5 Nm condition shows an average timing error of about 220 milliseconds. This means that assistance is activated approximately 0.22 seconds after motion onset. The 7 Nm condition shows an average timing error of about 125 milliseconds, so it is more quickly synchronized than the 5 Nm condition. For smoothness, the torque rate RMS is 19.4 Nm per second for 5 Nm and 24.6 Nm per second for 7 Nm. Both values are within the slew rate limit, so the torque is applied smoothly. Overall, the 7 Nm condition shows the largest EMG reduction and better timing synchronization. Therefore, the results indicate that hip extension assistance effectively reduces glute muscle activation during squat-based lifting. Thank you for listening.